For 60 years, we stared into the southern sky at that brilliant, beckoning point of light and called it hope. Alpha Centauri, our nearest stellar neighbor, a mere 4 light-years distant a cosmic stone's throw in the vast, dark ocean of the galaxy. Here, generations of astronomers, physicists, and dreamers pinned humanity's greatest aspiration, the first stepping stone to the stars. We discovered planets there, worlds nestled in the delicate orbital bands where liquid water could, in theory, exist. We imagined alien oceans shimmering under twin suns. We designed missions to reach them within a human lifetime, and we dared to believe that the universe had placed a potential new home for life right on our celestial doorstep. Then, we turned the most powerful telescope ever built toward that point of light. The James Webb Space Telescope, with its golden mirrors colder than the void, peered into the heart of our closest cosmic neighbor and saw something that shattered those dreams into stardust. The data that streamed back told a story, not of hospitality, but of violence as systemic, brutal fury that renders those promising worlds not just uninhabitable, but utterly, profoundly dead. What Webb found changes everything we thought we knew about our place in the cosmos and forces us to confront a disturbing new reality. If revelations like this, discoveries that rewrite our understanding of the universe, captivate you, then consider subscribing. Your support fuels this channel and brings more minds into these profound cosmic conversations. Now, let's begin this journey next door, to the world we thought we knew, and the terrible truth we now must face. Look up from the southern hemisphere, and you cannot miss it, the third brightest star in our night sky, a gleaming beacon in the constellation of Centaurus. That single point of light is a lie, a beautiful cosmic illusion. It is not one star, but 3, a triple star system, locked in a complex gravitational embrace, a mere 4.24 light-years from our solar system. The distance is almost incomprehensible in human terms, 25 trillion miles. A beam of light leaving Alpha Centauri tonight will not reach our eyes until 2029. If you boarded the fastest commercial aircraft, your descendants would live and die for 200,000 generations before glimpsing the destination. Yet, on the scale of our galaxy, which spans 100,000 light-years, Alpha Centauri is our next-door neighbor. If the Milky Way were the size of North America, the distance to Alpha Centauri would be the width of a city block. This proximity ignited our interstellar imagination like no other target. For as long as we have mapped the heavens, Alpha Centauri has captivated us. But the modern dream crystallized with the discovery of exoplanets. In 2016, the astronomy community erupted with news that seemed too perfect to be coincidence. Proxima b, a planet orbiting the smallest, dimmest member of the triple system, Proxima Centauri, a red dwarf star, invisible to the naked eye despite being our closest stellar neighbor. This world, about 1.3 times the mass of Earth, was found squarely in the habitable zone, that Goldilocks region where temperatures could allow liquid water to pool on its surface. Headlines proclaimed a potentially habitable world right next door. Scientists published papers speculating on its possible atmospheres, its potential for oceans, its capacity to host life. It was as if the universe, in a moment of generosity, had placed a waypoint for humanity's cosmic journey exactly where we needed it. The excitement fueled concrete plans. The Breakthrough Starshot Initiative, a bold vision funded by billionaires, proposed sending gram-scale probes propelled by powerful lasers to Alpha Centauri at 20% the speed of light. For the first time in history, sending a physical object to another star and receiving data back within a single human lifespan seemed not just possible, but plausible. The target was clear, the hope was tangible. We built the instrument to finally see our neighbor clearly. The James Webb Space Telescope, launched on Christmas Day 2021, is a technological marvel operating 1 million miles from Earth. Its primary mission, to gaze into the infrared universe, to see the heat signatures of distant worlds, and to dissect the chemistry of their atmospheres by catching starlight filtered through their alien skies. When a planet transits its star, a tiny fraction of the stellar light passes through its atmospheric envelope. Molecules within that atmosphere, water vapor, carbon dioxide, methane, Oxygen absorbs specific wavelengths of light, leaving unique chemical fingerprints in the spectrum. Webb is designed to read those fingerprints with godlike precision. Turning this mighty eye toward Alpha Centauri was an obvious, thrilling priority. We expected to refine our maps, to perhaps detect the blush of an atmosphere on Proxima b, to see the telltale signs of water vapor or the chemical imbalances that might hint at biology. We were ready to transform hopeful speculation into definitive knowledge. The data did not arrive as a gentle stream of discovery, but as a deluge of disquieting facts. What Webb revealed was not a habitable zone, but a kill zone. Proxima Centauri, that dim red ember, is not a gentle sun. It is a tempest. Webb's continuous monitoring, impossible from Earth's turbulent atmosphere, showed that this star is racked by stellar violence on a scale we had barely imagined. It unleashes massive flare events, not occasionally, but routinely, multiple times per week. These are not like our sun's modest solar flares. During an outburst, Proxima Centauri's brightness can increase by a factor of 100 or more, unleashing torrents of ultraviolet and X-ray radiation that would scour the face of any nearby world. A planet like Proxima b, orbiting 20 times closer to its star than Earth does to the Sun, receives the full, unfiltered force of this rage. The radiation intensity during these flares can be thousands of times the lethal dose for Earth life. The surface would be sterilized in minutes, its chemistry ripped apart. But the horror is not in the occasional storm, it is in the perpetual siege. Webb showed that these dramatic flares are merely the peaks of a constant, churning fury. Proxima Centauri's fully convective, interior a seething, boiling pot, unlike our sun's layered structure, generates a magnetic dynamo of relentless violence. The planet is not periodically battered. It exists in a state of permanent bombardment. This stellar violence has a clear and irreversible consequence. Webb's sophisticated spectroscopic instruments turned toward Proxima b, searching for the chemical signatures of an atmosphere. They searched for the dip in starlight caused by nitrogen, oxygen, carbon dioxide, water vapor, the markers of a world that could possibly nurture life. The data returned a profound and chilling result. Nothing. The spectra were flat, featureless. Proxima b either never developed a substantial atmosphere, or more likely, any atmosphere once possessed has been utterly stripped away by billions of years of relentless stellar wind and radiation blasts. The planet now stands as a bare, airless rock, a silent moon-like world where the stellar wind blows directly on the surface, where ultraviolet light bakes the stone unfiltered, where temperatures swing between the scorching hell of permanent daylight and the deep freeze of eternal night on its tidally locked face. The promise of Proxima b, the symbol of hope for a generation, evaporated under Webb's cold, unblinking gaze. It is not a stepping stone. It is a tombstone, a warning written in the anti-lines of a light spectrum. And as disturbing as this revelation was for our red dwarf neighbor, the telescope was just beginning its survey of the Alpha Centauri system. The larger, sun-like stars, Alpha Centauri A and B, still held potential. Surely, in their more stable orbits, farther from stellar tantrums, a true haven could exist. But to understand the full, devastating picture Webb would paint, we must first delve deeper into the specific hellscape it revealed around Proxima, and comprehend why this single finding forces us to rewrite the story of life in the cosmos. The hope for Proxima b was always tempered by a quiet scientific unease. Red dwarf stars like Proxima Centauri are the universe's misers and tyrants. They comprise nearly 3/4 of all stars in the Milky Way, burning their scant hydrogen fuels so slowly that their lifetimes stretch into trillions of years, dwarfing the mere 10 billion year span of a star like our Sun. This incredible longevity once seemed like a gift to potential life, an almost infinite timeline for evolution to work its wonders. But longevity comes with a catastrophic cost. The very nature of a red dwarf's existence makes it a perpetually hostile parent. To understand the doom of Proxima b, we must descend into the churning heart of its star. Our Sun is a relatively orderly sphere. Energy generated by fusion in its core migrates outward through a radiative zone. a slow, stately procession of photons that can take hundreds of thousands of years to reach the surface. This creates a buffer, a stability that moderates the star's external behavior. A red dwarf has no such buffer. Its smaller mass means its interior is entirely convective. Imagine a pot of water boiling violently on a stove. Hot plasma from the core rockets directly to the surface, cools, and plunges back down in a continuous chaotic churn. This constant turmoil generates immensely powerful and complex magnetic fields. These magnetic fields become twisted, tangled, and stressed beyond endurance, and when they snap reconnecting into simpler, lower energy configurations, they release that stored energy in cataclysmic outbursts, stellar flares. The flares from our sun are, by comparison, gentle size. A major solar flare might increase the sun's brightness by a fraction of a percent for a few hours. What James Webb witnessed at Proxima Centauri was of a different cosmic magnitude. Webb's sensitive infrared detectors, monitoring the star for weeks on end, recorded flares that boosted the star's brightness by factors of hundreds. In the most extreme events, the star's output in certain X-ray and ultraviolet wavelengths spiked by 10,000 times or more. The energy released in a single one of these paroxysms is equivalent to tens of millions of the most powerful thermonuclear weapons humanity has ever detonated, all exploding at once. And Webb's relentless gaze revealed the most disturbing fact. This isn't rare. It is the star's default state. Proxima Centauri experiences significant flare events several times a week, with smaller microflares crackling across its surface daily. There is no calm. There is only the brief, deceptive lull between tempests. Now, project this reality onto Proxima b. The planet orbits its dim star incredibly close, just 7.5 million kilometers, completing a year in a mere 11.2 Earth days. This proximity, necessary to bask in enough warmth for liquid water, also places it in the heart of the magnetic storm. When a flare erupts, the planet is not merely illuminated, it is immersed. The blast of high-energy photons, ultraviolet and X-rays arrives at the planet's day side in minutes. These photons carry enough energy to break apart molecular bonds, a process called photodissociation. They rip water vapor into hydrogen and oxygen. They tear carbon dioxide apart. They shred complex organic molecules into inert components. But the violence is not merely photonic. The flares also eject vast clouds of charged particles, protons and electrons, accelerated to nearly the speed of light. This stellar wind from Proxima Centauri, Webb's spectroscopy confirmed, is hundreds of times denser and more energetic than our sun's solar wind at an equivalent relative distance. For Proxima b, lacking a substantial magnetic field as Webb's data implies, this wind does not deflect, it impacts. The surface of Proxima b is thus subjected to a continuous multi-front assault. Imagine standing on its sun-scorched dayside. The very rock beneath your feet would be chemically altered by the radiation, a process called space weathering that darkens and breaks down minerals. The sky, if any tenuous haze existed, would not be blue, but a permanent, lethal glow of ionized particles and scintillating radiation. Any atmosphere is not merely thinning, it is being actively blasted away. The high-energy photons heat the top of any atmospheric layer, giving atoms and molecules the kinetic energy to escape the planet's gravity. The stellar wind particles act like a cosmic sandblaster, physically sputtering away atmospheric gas by direct impact. This is not a slow leak over billions of years. It is a high-pressure hose directed at a cloud of smoke. Calculations based on Webb's intensity measurements suggest an Earth-like atmosphere would be completely stripped from Proxima b in well under 100 million years. The planet is 4.8 billion years old. It has been airless for almost its entire existence. This leads to the second horrific condition confirmed by Webb's thermal maps: tidal locking. A planet so close to its star feels an immense gravitational gradient. Over time, the star's tidal forces act as a brake, slowing the planet's rotation until it matches its orbital period. One hemisphere faces the star forever a perpetual, blistering day. The other faces the eternal, frigid night of deep space. Proxima b has been locked in this embrace for eons. Webb's measurements of the minute difference in infrared heat emission between the planet's day side and night side revealed a temperature differential of over 1,000 degrees Celsius. The day side is likely hotter than the melting point of lead. The night side is colder than Pluto, where even carbon dioxide freezes solid into dry ice snow. On a world with a thick, circulating atmosphere, winds might transport heat from the day side to the night side, moderating these extremes into a potentially habitable twilight ring. But an airless world has no such mechanism. The heat does not travel. The day side bakes, the night side freezes. There is no gentle gradient, only the stark, impassable cliff of temperature at the terminator line. This is not a world that could host a global biosphere. It is a study in thermodynamic extremes, a sterilized rock split between a furnace and a cryogenic vault. The habitable zone around a red dwarf, it turns out, is a cruel paradox. To be warm enough for liquid water, a planet must orbit so close that it becomes tidally locked and is subjected to the full, unrelenting fury of the star's magnetic personality. The conditions for liquid water and the conditions for atmospheric survival are mutually exclusive. Webb's data didn't just find Proxima b uninhabitable. It revealed a fundamental flaw in our concept of habitability for the most common star type in the galaxy. Every promising Earth-sized planet detected orbiting in the habitable zone of a red dwarf now stands under this same shadow of profound doubt. The dream of billions of potential life-bearing worlds around these abundant stars begins to evaporate, leaving behind a much lonelier, harsher cosmic landscape. The most definitive, and in many ways the most haunting, evidence from James Webb came not from images, but from absence. Spectroscopy is the telescope's superpower, the ability to dissect light into its constituent colors, revealing the chemical fingerprints of the universe. When Webb turned his power toward Proxima b during a transit, astronomers expected to see, at the very least, the subtle dip in starlight that would indicate something was enveloping the planet. An atmosphere, even a thin or alien one, leaves a mark. The molecules within it absorb specific, precise wavelengths of the star's light as it filters through. A thick, Venus-like carbon dioxide haze would block broadly across the infrared. Water vapor would create a distinctive pattern of absorption lines. Methane, a potential biosignature, would leave its own subtle signature. The computers and scientists waited, sifting through the exquisite data, looking for these telltale lines, the scribbled notes of a world story in the spectrum. They found a blank page. The transit signature of Proxima b was clean, sharp, and featureless. The starlight dimmed exactly as it would if a bare, airless rock passed in front of the star and then returned to normal. There were no atmospheric lines, no chemical fingerprints, nothing. This null result was, in its way, louder than any detection. It meant that Proxima b's atmosphere, if it ever had one, is gone beyond trace. It is a ghost, vanished into the interstellar void. This spectroscopic silence allows us to reconstruct the planet's grim history with frightening clarity. In its youth, freshly formed from the circumstellar disk, Proxima b likely possessed a primordial atmosphere, a thick envelope of hydrogen and helium, along with volatiles like water vapor, carbon dioxide and nitrogen vented from its hot interior. But from its very first orbit, it was under attack. The young Proxima Centauri was even more violent than it is today, in a phase called the pre-main sequence ramp-up, where it likely burned even brighter in destructive ultraviolet light. The planet's infancy was spent in a stellar temper tantrum. The process of atmospheric annihilation is a multi-pronged assault, and Webb's data allows us to quantify each mechanism. First, photoevaporation. The intense, high-energy UV and X-ray radiation from the star pumps enormous energy into the upper atmosphere. Molecules are not just dissociated, their atoms are heated to such high temperatures that they achieve escape velocity, flying off into space. Light elements like hydrogen are the first to go, but even heavier atoms can be lost over time. Second, sputtering. The relentless stellar wind, a supersonic flow of charged particles, doesn't just flow past. It slams into the atmospheric particles. Think of it not as a wind, but as a barrage of microscopic bullets. These collisions knock atmospheric atoms and molecules upward, giving them the momentum to escape the planet's gravitational pull. Third, ion pickup. If the planet lacks a strong global magnetic field, as a slowly rotating, tidally locked world almost certainly does, the stellar wind's magnetic field can interact directly with ionized particles in the upper atmosphere, accelerating them and sweeping them away like leaves in a hurricane. On a world like Earth, these processes are mitigated. Our magnetic field acts as a shield, deflecting the bulk of the solar wind around our planet. Our atmospheric ozone layer absorbs much of the damaging UV radiation. Our planet's rapid rotation and large molten core sustain that magnetic dynamo. Proxima b had none of these defenses. Tidal locking doomed its magnetic field. The constant radiation prevented the chemical stability needed to form an ozone-like layer. It was naked from the start. Webb's non-detection tells us the stripping process reached its conclusion long ago. All the water that might have once condensed on its surface or lingered in its crust has been dissociated by UV light. The lightweight hydrogen escaped to space. The oxygen likely rusted into the surface rocks or was lost as well. Any carbon dioxide was photo-dissociated or frozen out on the permanent night side. The nitrogen, if it ever existed, is gone. This transforms our understanding of the planet's surface. Without an atmosphere, there is no pressure to keep liquid water stable. Even if a trickle of water somehow emerged from the interior onto the dayside, it would instantly boil away in the near vacuum. Its molecules rapidly lost to space. Without an atmosphere, there is no shield against meteoroids. The surface would be a pockmarked lunar landscape, but one also heavily irradiated and chemically altered. Without an atmosphere, there is no sound, no weather, no soft glow of sunrise, only the stark, silent, and lethal contrast between the blinding stellar fury in a black sky and the absolute, star-studded darkness of the frozen night. Proxima b is not a world that lost its chance at life. It is a world where the conditions for life were never permitted to exist for more than a fleeting geological moment. The habitable zone in this case was a death sentence. The implications of this single, airless world ripple outwards, casting a pall over the thousands of similar candidates discovered orbiting red dwarfs throughout our galaxy. If our nearest example is this barren, how many others share its fate? The hope for life around the most common stars in the universe begins to dim, replaced by a new, stark model of planetary sterility. But the Alpha Centauri system still held two other stars, both seemingly more benign, more sun-like. Perhaps there, in the stable light of a friendly sun, a true oasis waited. The next phase of Webb's investigation would turn its golden mirrors toward the binary dance of Alpha Centauri A and B, where the promise was even greater, and the ensuing disappointment would reveal a different kind of cosmic cruelty. Not the violence of a star, but the chaos of gravity itself. Shifting its gaze from the furious red dwarf, James Webb turned toward the primary pair of the system, Alpha Centauri A and B. Here, the view was classically beautiful, reminiscent of home. Alpha Centauri A is a near twin of our Sun G-type yellow star, slightly more massive and about 50% brighter. Its light, viewed through Webb spectrometers, revealed an almost identical chemical composition to our own star, a sibling forged from the same galactic ingredients. Alpha Centauri B, its partner, is a K-type orange star, slightly smaller and cooler than the Sun, but still a stable nuclear furnace of the kind we understand. From a distance, this binary pair offered the most Earth-like conditions imaginable beyond our solar system, the habitable zones. The orbital bands where a planet could have liquid water lie at comfortable Earth-like distances, far from the tidal locking proximity of Proxima b. Here, a planet could rotate freely, enjoy a normal day-night cycle, and bask in steady, sun-like light. The dream of a terrestrial world with twin suns in its sky. A real-world Tatooine seemed not just possible, but probable. Earlier, tentative observations had even hinted at possible planetary candidates. The hope was that Webb would now bring these worlds into clear focus, revealing them as the true jewels of the system. But to understand the fate of planets around Alpha Centauri A and B, one must first understand their dance. They are not distant relatives loosely bound. They are intimate partners in a complex gravitational embrace. They orbit their common center of mass in an elliptical path that brings them as close as 11 astronomical units, AU, roughly the distance from the Sun to Saturn, and as far apart as 36 AU, about the distance to Pluto. They complete this dance once every 79 years. This proximity is what makes them shine as a single brilliant beacon in our sky. It is also what doomed any chance for stable, habitable planets from the very beginning. The disruptive power of a binary companion on planet formation is not a gentle nudge. It is a periodic gravitational hammer blow. Every 79 years, as the stars swing through their closest approach, their combined gravity creates a zone of profound instability that reaches deep into the space around each star. Any collection of dust, rocks, or nascent planets trying to coalesce within this zone would be subjected to rhythmic, catastrophic perturbations. James Webb did not find clean, stable, habitable zones around these stars. Instead, its infrared eyes found the forensic evidence of a crime scene in the aftermath of gravitational murder. Webb detected faint, telltale infrared excess around both stars, the signature of a debris disk. But this was not the rich, dense disk of a young system busy building planets like our solar system once had. This was a sparse, anemic ring of cold dust and shattered remnants, confined to distances far beyond where terrestrial planets could form. The inner regions, precisely where the habitable zones of both stars reside, were conspicuously empty. Not just empty of planets, but empty of the very building blocks needed to make them. The dust and gas that should have populated these regions billions of years ago were gone. Webb's data painted a clear picture. The protoplanetary disks that once swirled around both Alpha Centauri A and B were violently disrupted and truncated in their youth. The gravitational tides from the companion star acted like a cosmic blender, stirring up the material, increasing collision velocities, and preventing the gentle accretion that turns dust grains into pebbles, pebbles into planetesimals, and planetesimals into worlds. Computer models of such binary systems had long predicted this outcome. The physics is unforgiving. In a single star system like ours, particles in a disk orbit on nearly circular, coplanar paths, collisions are slow and gentle, often resulting in sticking and growth. Introduce a massive binary companion on an elliptical orbit, and everything changes. The companion's gravity periodically tugs on every particle in the disk. Orbits become excited, more elliptical and tilted relative to each other. When these perturbed orbits intersect, collisions are no longer gentle. They occur at speeds of kilometers per second, speeds that shatter and vaporize rather than merge. The process is one of destructive grinding, not constructive accretion. The habitable zone, being at an intermediate distance, suffers the worst of this chaos. Material is either flung inward to be swallowed by the star, ejected outward into the cold periphery, or blasted into dust fine enough to be pushed away by stellar radiation pressure. Webb's observation of the debris disk's inner edge lying far outside the habitable zone is the smoking gun for this process. The region where life could potentially thrive was systematically scoured clean before the first planet could even be born. This revelation carries a profound and ironic sadness. The very thing that made Alpha Centauri A and B so bright and prominent in our sky, their close binary nature, is what rendered them sterile. Their luminous partnership, a beautiful dance from our vantage point, was a cataclysm for any fledgling planets. The dream of a stable Earth analog orbiting either of these suns crumbles under the relentless laws of orbital mechanics. There is no stable solution, no magical Lagrange point, where a planet could peacefully exist within the habitable zone for billions of years. The gravitational perturbations accumulate over time, inevitably driving any hypothetical planet into a star-grazing or star-ejecting orbit on timescales of millions of years, a mere blink compared to the billions of years required for life to emerge and evolve. The binary stars and their brilliant close waltz created a zone of permanent chaos, a forbidden garden where nothing could ever take root and grow. The promise of our sun-like neighbors was an illusion, shattered by Webb's precise measurements. But the story of the Alpha Centauri system's sterility was not yet complete. There remained the mysterious relationship of the third star, the distant, violent Proxima, to its brighter siblings. How did this chaotic family come to be? And did its violent formation history deliver a final, killing blow to any lingering hope? The answer would lie in the orbital dynamics of the triple system itself, a clue hidden in Proxima's wide, lonely path. The final piece of the puzzle, revealed by Webb's long baseline astrometric measurements and deep spectroscopic surveys, concerned the origin of the system itself. The current configuration, too, sun-like stars in a tight binary, with a violent red dwarf in an enormous half-million-year orbit, is not a common one. It speaks of a violent past. The leading theory, now strongly supported by Webb's data, is that Proxima Centauri was not born with Alpha Centauri A and B. It was an orphan, a lone red dwarf wandering the galactic neighborhood that was later captured by the binary pair's gravity. Webb's precise analysis of Proxima's motion and composition subtly differs from that of A and B, suggesting it formed in a different stellar nursery. Its capture was a dramatic, slow-motion cosmic event. As Proxima drifted near the binary, the complex three-body gravitational interaction robbed it of just enough kinetic energy to trap it in a wide, looping orbit. But energy in a gravitational system is conserved. It doesn't disappear. The kinetic energy lost by Proxima had to be transferred somewhere else. The only available sinks were the binary stars themselves, and, crucially, any material orbiting them. This capture event, occurring likely hundreds of millions of years after the formation of A and B, would have been the final, sterilizing cataclysm for the system. Imagine the scene: the binary pair, having already disrupted their own protoplanetary disks into sparse debris rings, might still have had a handful of surviving planetesimals, or even nascent protoplanets on marginally stable orbits in their outer reaches. The gravitational tsunami of Proxima's close passage would have swept through this fragile architecture like a bull through a china shop. Orbits already made precarious by the binary's influence would have been violently destabilized. Any larger bodies would have been sent careening into their host stars, ejected into the blackness of interstellar space, or shattered in catastrophic collisions. The debris disk we see today around A and B is not the primordial disk. It is likely the second-generation wreckage from this final gravitational purge, the dusty remains of what little survived the initial binary disruption, only to be ground to powder during Proxima's capture. Webb's spectroscopic analysis of this debris dust provided the final grim clue. The dust is primarily composed of silicates, the stuff of dry rock. It shows a conspicuous lack of the ices and hydrated minerals that would indicate water-rich building blocks. In our solar system, the asteroid belt, and especially the distant Kuiper belt, are reservoirs of water ice, delivered to the inner planets during the late heavy bombardment. The Alpha Centauri system, it seems, lacks this critical water reservoir. The combined effects of the binary's early heating and stirring, and the later gravitational cleansing from Proxima's capture, either drove off these volatile ices entirely, or sequestered them in bodies so distant and sparse that they could never hydrate or form in terrestrial world. A planet that somehow managed to coalesce in this system would have been born, dry, a desiccated rock without the most crucial ingredient for life as we know it. The narrative that emerges is one of compounded catastrophe. First, the binary nature of A and B destroyed the possibility of stable planet formation in their habitable zones, grinding potential worlds to dust. Second, the captured red dwarf Proxima delivered a late-stage gravitational shock that purged the outer system of leftover building blocks and any surviving large bodies. Third, Proxima itself, by its very stellar nature, renders its own immediate vicinity a radiation hellscape, stripping any close-orbiting world like Proxima b of its atmosphere and water. From the inner orbital embrace of the red dwarf to the sun-like reaches of the binary pair, the Alpha Centauri system is a multi-layered death trap. It is a stellar neighborhood where every possible avenue to habitability, stable orbits, atmospheric retention, water delivery, and chemical evolution has been systematically blocked by fundamental astrophysical processes. Webb's comprehensive survey did not merely fail to find life. It revealed a system architecturally designed to prevent life's very existence. This forces a monumental shift in perspective. Our nearest cosmic neighbors are not a template for what is common, but a cautionary tale of what is likely. If a system this seemingly promising, this close, can be so thoroughly sterile, what does it imply for the rest of the galaxy? The search for life must now contend with a universe that appears not just vast, but profoundly, intimidatingly hostile. The final chapters of this discovery explore the crushing implications of this loneliness, forcing us to rewrite our place in the cosmos and confront the terrifying possibility that islands of life like Earth are not just rare, but almost impossibly isolated. The fate of Proxima b and the barrenness of the Alpha Centauri binary system, while rooted in different causes, stellar violence and gravitational chaos ultimately converge on the same existential threat, a relentless radiation environment that forms an inescapable prison for habitability. James Webb's instruments, particularly those designed to measure high-energy phenomena, allowed scientists to quantify this prison in horrifying detail, constructing a panoramic view of systemic sterilization. Beyond the spectacular flares, Webb mapped the constant baseline radiation output from all three stars. Proxima Centauri's stellar wind, a stream of charged particles, was measured to be hundreds of times denser and more energetic than our suns at equivalent orbital distances. For a planet like Proxima b, this wind doesn't flow around a magnetic shield, it batters the surface directly. This sputtering effect alone over billions of years could erode away entire oceans worth of material, atom by atom, blasting them into space. But the wind is just one wall of the prison. Webb's ultraviolet and X-ray spectrometers revealed the second wall, photolytic butchery. The UV flux from Proxima, even during its quiet periods, is orders of magnitude more intense than Earth's. This radiation doesn't just heat, it dissociates. It breaks apart the complex organic molecules that are the precursors to life: amino acids, nucleotides, lipids with ruthless efficiency. Laboratory experiments show such molecules can be destroyed in hours under far weaker UV fields. On Proxima b's surface, the formation of these compounds would be like trying to build a house of cards in a hurricane. They are torn apart faster than any natural process could assemble them. This nullifies the very possibility of prebiotic chemistry, the essential first step toward biology. There is no primordial soup here. There is only a sterilizing broth of high-energy photons. But what of refuge? On early Earth, life is thought to have originated in deep ocean vents or subsurface aquifers, shielded from harsh surface radiation. Could similar niches exist on these doomed worlds? Webb's data on penetrating radiation closes this last door of hope. The high-energy protons from stellar flares and cosmic rays, amplified by the system's lack of a protective heliosphere, can penetrate hundreds of meters of rock or water. While a deep aquifer might offer some protection from UV, it would still be permeated by this ionizing radiation, damaging biomolecules and disrupting cellular processes. Furthermore, a subsurface ecosystem requires a flow of chemicals and energy from the surfacer connection to a larger planetary geochemical cycle. On an airless, desiccated world like Proxima b, or a geologically dead world stripped of its volatiles, these life-sustaining cycles do not exist. The subsurface is not a refuge. It is a sealed, radioactive tomb. The prison extends to Alpha Centauri A and B as well, though its bars are differently fashioned. While their stellar winds and UV output are more sun-like, the binary interaction creates unique hazards. As the two stars orbit, their stellar winds collide, creating shock zones of compressed, turbulent plasma and intensified magnetic fields. Any planet orbiting one star would periodically pass through these maelstroms, suffering sudden, dramatic spikes in particle radiation that would violently strip its atmosphere in pulses, preventing any long-term stability. The habitable zone, therefore, is not a safe harbor, but a region periodically swept by gravitational and radiative storm surges. Webb's most profound contribution was to move these threats from theoretical concerns to measured, quantified realities. We now have data on flare energies, wind densities, UV flux levels, and particle penetration depths. We can plug these numbers into models of atmospheric loss and chemical evolution. the results are unequivocal. The timescales for destruction are vastly shorter than the timescales required for the emergence of life. Atmospheric stripping occurs over millions to tens of millions of years. The complex chemical evolution leading to the first self-replicating molecule on Earth likely required hundreds of millions of years of stable, protected conditions. In the Alpha Centauri system, the destructive processes win the race every single time. The window of opportunity for life never opens. It is welded shut from the outside by the physics of the stars themselves. This transforms the habitable zone from a useful shorthand into a potentially tragic misnomer. It identifies where liquid water could exist based on temperature alone, ignoring the far more critical factors of atmospheric retention, radiation shielding, and chemical stability. What good is liquid water if the atmosphere needed to keep it liquid is gone, or if the complex molecules needed for life are instantly shredded by the very light that provides the warmth? The Alpha Centauri system stands as a stark monument to this cosmic truth, revealing that the universe is not merely indifferent to life, but in most configurations, actively and efficiently hostile to it. This realization forces us to perform a painful, wholesale revision of the cosmic census, a recalculation that shrinks the galaxy from a presumed buzzing hive of potential life to a much darker, much quieter place. The implications of James Webb's findings at Alpha Centauri do not remain confined to a single star system 4 light-years away. They send shockwaves through our entire understanding of the galaxy, forcing a radical and sobering reassessment of where life could possibly exist. For decades, optimistic estimates, fueled by the discovery of thousands of exoplanets, suggested the Milky Way could harbor tens of billions of potentially habitable worlds. The Alpha Centauri results act as a series of severe correction factors, drastically reducing that number. The first and largest correction concerns red dwarf stars, which make up roughly 70% of the galaxy's stellar population. Proxima Centauri is not an anomaly, it is the archetype. Webb surveys of other red dwarfs show that such extreme magnetic activity, flaring, and dense stellar winds are the norm for this stellar class, especially during their first several billion years, precisely when life would need to gain a foothold. The fundamental architecture of a red dwarf fully convective, with a habitable zone requiring extreme proximity dooms, the habitability of any terrestrial planet within it, the conditions for liquid water, and the conditions for atmospheric survival are mutually exclusive. Therefore, we must effectively cross off the vast majority of red dwarfs as potential hosts for complex surface-dwelling life. This single stroke eliminates nearly 3/4 of all stars from the optimistic tally. The second correction concerns binary and multiple star systems. Approximately half of all Sun-like stars are in such configurations. Alpha Centauri A and B represent a common binary separation tens of astronomical units. Webb's observations of other similar binaries show the same pattern: truncated debris disks, cleared inner regions, and a severe lack of stable orbital real estate in the habitable zone. While some binaries with extremely tight or extremely wide separations might allow for planets, the disruptive middle ground occupied by our nearest neighbors appears to be common. This means a significant fraction of the remaining 30% of Sun-like stars are also poor candidates for hosting stable, long-term planetary systems conducive to life. Now, consider the survivors, a minority of single, Sun-like stars, G and K types. Even for these, the hurdles remain immense. The planet must form with the right size and composition, a rocky world with a substantial iron core for a magnetic dynamo, form with or acquire by comet/asteroid bombardment a vast amount of water, orbit within a narrow, stable band for billions of years, develop and maintain plate tectonics for climate regulation and geochemical cycling, be fortunate enough to avoid sterilizing events like nearby supernovae, gamma-ray bursts, or catastrophic asteroid impacts during its early, fragile, biotic phase. Each of these is a filter, the product of all these probabilities, each likely far less than one results in a number that is astronomically small. This forces a dramatic revision of the Drake equation, the famous formula estimating the number of communicative civilizations in the galaxy. The variable f dumbus das with planetary systems remains high, But the variable n on Stogger E, number of planets per star that can support life, must now be drastically reduced. We thought it might be a number like 0.1 or even 1 for some stars. The Alpha Centauri data suggests that for most stars, it is effectively 0. For the rare, single, quiet star, it might be 0.01 or less. This correction propagates through the rest of the equation. If the number of truly habitable planets in the galaxy is not in the billions, but perhaps in the millions or even the thousands, then the subsequent probabilities for the emergence of life, intelligence, and technology make the final number of coexisting civilizations vanishingly small, perhaps single digits across the entire Milky Way. This perspective resolves with cold, logical finality the Fermi paradox. Where is everybody? The answer implied by Webb is they are almost nowhere. The silence of the cosmos is not because civilizations hide or destroy themselves or use undetectable technology. It is because civilizations, and even simple life, are phenomenally rare occurrences in a galaxy that is, for the most part, a beautiful but barren graveyard of sterile rocks and violent stars. The great distances between these rare oases of biology are so vast that contact or even detection becomes a near impossibility. We are not failing to hear their signals because our telescopes are too weak. We are failing to hear them because, in our galactic neighborhood, there is likely no one there to send them. This realization transforms our cosmic status from presumptive members of a galactic community to the likely isolated inhabitants of a precious, fragile island in a vast and empty sea. The profound silence that greeted our radio telescopes for decades now takes on a new and heavier meaning in the light of Webb's Alpha Centauri data. The search for extraterrestrial intelligence, SETI, was founded on optimism, the belief that the universe was teeming with technological species, and we just needed to listen on the right frequency. The null result after over 60 years of searching was often explained away by technical challenges. We hadn't looked long enough in the right way, or perhaps advanced civilizations use communication methods beyond our comprehension. The Alpha Centauri findings suggest a more fundamental and darker explanation. The Great Filter is behind us, and it is largely environmental. The Great Filter is a concept in Fermi paradox discussions, some stage in the progression from non-life to spacefaring civilization, is extremely unlikely or fatal. The Alpha Centauri evidence strongly indicates that one of the most powerful filters is the formation of a stable, long-term habitable environment itself. The list of requirements: a stable single star, a planet in a precise orbit with the right composition, water, a magnetic field, plate tectonics, and freedom from sterilizing cataclysms appears to be a chain of improbable miracles. Our solar system passed through this filter. Alpha Centauri, in 3 different and devastating ways, did not. If our nearest, most promising neighbor failed, then the failure rate across the galaxy must be staggeringly high. This reframes humanity's situation. We are not a young, backward species struggling to catch up to a chorus of galactic elders. We may, in fact, be an extraordinary rare, perhaps even unique, phenomenon within thousands of light years. The silence is not a mystery. It is the expected background state of the universe. It means that when we look at the stars, we are not looking at the twinkling lights of future allies or adversaries. We are looking at the watchfires of empty camps, the lighthouses on desolate shores. This isolation carries a monumental responsibility. If Earth is one of a handful of conscious oases in this galactic desert, then its value is incalculable. There is no planet B at Alpha Centauri. There may be no viable planet B within 100 or 1,000 light years. The dream of interstellar colonization as an escape hatch for a troubled Earth suddenly seems not just technologically daunting, but tragically naive in its assumption that viable destinations exist within reach. Furthermore, it suggests that if we do eventually detect a signal or a techno-signature, it would likely be from a civilization so distant thousands or tens of thousands of light years away that two-way communication is impossible. We would be receiving a fossilized message from a civilization that may have risen and fallen when humanity was in the Stone Age. They would be ghosts in the cosmic microwave background, not conversation partners. The dream of a galactic community shatters against the hard rocks of distance and time. This isolation forces a profound philosophical shift. For centuries, since Copernicus dethroned us from the center of the universe, science has consistently revealed our cosmic mediocrity and average planet around an average star in an average galaxy. Webb's findings Alpha Centauri introduce a startling counterpoint. In one critical aspect, the possession of a complex, conscious biosphere, we may be utterly extraordinary. This doesn't return us to a pre-Copernican specialness, but it replaces mediocrity with precious rarity. We are not at the center, but we may be a jewel of near-unique brilliance in a vast, dark vault. This knowledge must inform our future. It makes the preservation of our planetary biosphere not just a political or environmental issue, but a cosmic imperative. If the filter behind us is so severe, the one ahead of us, the filter of self-destruction through war, environmental collapse, or technological catastrophe becomes the defining challenge of our species. Passing through it is no longer just about our own survival. In a very real sense, it becomes about preserving one of the universe's rarest and most marvelous creations, conscious awareness itself. The science from our nearest stars is no longer a puzzle to be solved, but a lesson to be learned. It is a lesson in fragility, in rarity, and in the overwhelming duty that comes with the incredible good fortune of our existence. The final, enduring image from the James Webb Space Telescope's investigation of Alpha Centauri is not one it directly captured. It is the implied image, reflected back at us from the data of our sterile neighbors, the vision of Earth, seen from a cosmic perspective, newly informed by profound loneliness. Our planet is no longer merely habitable. It is revealed as a statistical miracle, a cosmic oasis of staggering improbability. Every condition that Alpha Centauri lacks, Earth possesses in delicate dynamic balance. Consider the defenses our world marshals against the cosmic hostility so starkly displayed next door. Our Sun is a stable, solitary star with a moderated magnetic cycle. Its habitable zone is a broad, welcoming band. Our planetary orbit is nearly circular and stable over billion-year timescales. Our large moon stabilizes our axial tilt, preventing chaotic climate swings. Our active iron core generates a powerful magnetic field that deflects the solar wind, carving out a protective cocoon, the magnetosphere, without which our atmosphere would erode like Mars's. Our atmosphere, with its UV-absorbing ozone layer and temperature-moderating greenhouse gases, provides both shield and blanket. Our plate tectonics continuously recycle carbon, regulating long-term climates and replenishing nutrients. Our planet formed with and retained vast oceans of water, the universal solvent for biochemistry. And somehow, from this uniquely favorable confluence, life emerged, persisted, and evolved into a species capable of building a telescope to discover just how rare it all is. The Alpha Centauri system serves as the perfect control experiment. It shows us what happens almost inevitably when even a few of these conditions are absent. No magnetic field, atmosphere stripped, wrong star type, sterilizing radiation. A binary companion, orbital chaos, and a shattered nursery. The contrast could not be more extreme. We are not living in a typical cosmic environment. We are living in the exception. This realization transforms our relationship with the universe. The cosmic loneliness it implies is not a cause for despair, but for a profound and sobering maturity. It ends our childish fantasy of a galaxy filled with friendly aliens or empty planets waiting for us to claim them. It forces us to grow up, cosmically speaking. We are on our own. The future of mind, meaning, and perhaps even morality in this corner of the universe appears to rest solely on our shoulders. The project of civilization is not a rehearsal. It is the main, and possibly the only, act on a vast, dark stage. This grants a new, almost sacred significance to the stewardship of our planet. Environmentalism is not merely about saving polar bears or preserving beautiful landscapes. It is about safeguarding a phenomenon of cosmic significance. Climate change, biodiversity loss, and pollution are not local problems. They are the processes by which a rare and precious cosmic jewel risks being dimmed or even shattered. by its own awakening consciousness. The silence from Alpha Centauri is a warning whisper across the light years. This is all you have. There is no backup, there is no rescue. You must succeed here. For the dream of space exploration, the goalposts have moved, but the dream is not dead. It is refined. The target is no longer a nearby twin of Earth, for none exists next door. The goal becomes more profound, to learn to sustain life independently of Earth, not as an escape, but as an extension of our biosphere's resilience. To build arcs, not because we are abandoning a sinking ship, but because we are cherishing a precious flame enough to carry it elsewhere. The destinations will be farther, the voyages longer, the challenges greater. We go not to find neighbors, but to ensure that the phenomenon of life, having beaten staggering odds to emerge here, does not perish here. James Webb, by showing us the dead, silent nature of our nearest stellar neighbors, has performed the ultimate act of cosmic mirror-holding. It has shown us the terrifying, beautiful truth of our isolation. In doing so, it has not diminished humanity, but has elevated the significance of our existence and the weight of our choices to a cosmic scale. The universe is not hostile by intention. It is simply governed by laws that make life an exquisite accident. We are that accident, awake and gazing back at the void. What we do with that consciousness, on this pale blue oasis, is now the most important story being told in this galaxy. The search for life continues, but henceforth, it will be pursued with the humbling knowledge that every new sterile world we find only makes our own living planet, and our responsibility for it, more astonishing and more sacred. The story of Alpha Centauri is not a story of an ending. It is the story of a beginning, the beginning of a true, mature understanding of our place in the cosmos, a place of profound solitude, infinite wonder, and ultimate responsibility. The data is analyzed, the papers are published, the stunning, beautiful, and disturbing portrait of the Alpha Centauri system is complete. James Webb's work there is done. Its mirrors now turn to other cosmic mysteries, but the echo of what it found next door reverberates not just through scientific circles, but through the very foundation of how we see ourselves. We have received the ultimate report on our cosmic neighborhood, and the verdict is one of profound, echoing silence. This silence, however, is no longer empty. It is now filled with meaning, a meaning we must decipher. For centuries, the human story has been one of seeking connection. We navigated by the stars, told myths about them, and eventually dreamed of visiting them. Alpha Centauri was the physical embodiment of that dream, the closest harbor in the endless sea. Webb has shown us that harbor is an illusion, a mirage of deadly rocks and violent suns. The first great lesson of this discovery is the death of a certain kind of innocence. We must relinquish the childhood fantasy of a universe waiting for us, populated with friends or foes. We are confronted with the mature reality of a universe that is, in its essence, magnificent, physical, and largely inhabitable. The dream of interstellar expansion as a near-future endeavor, of hopping to a new world within a lifetime, has collided with the immutable laws of physics and probability. The journey will be far longer, to destinations far more distant, if it is possible at all. This could be seen as a cause for despair, but that would be a misreading of the revelation. Instead, it grounds our ambition in reality and refocuses our purpose. The project of humanity is not, and perhaps never was, about finding a ready-made galactic community to join. The project is about building a sustainable civilization here, and eventually carrying the principles of that sustainability with us as we learn to survive beyond our cradle. The challenge is infinitely harder than we hoped, which makes the endeavor infinitely more significant. We are not moving to a new house. We are learning the profound art of maintaining the only home we have, while painstakingly crafting vessels that might one day carry its essence outward. The second and heavier lesson is that of cosmic responsibility. If the filter for complex conscious life is as severe as the Alpha Centauri data suggests, then Earth is not just our home, it is a museum of singular wonders. A library containing the only known copy of a story billions of years in the making, and a fragile garden in a desert that spans light years. Every extinction we cause, every ecosystem we degrade, every climate system we destabilize is not a local affair. It is the degradation of something that, for all we know, may be unique in this quadrant of the galaxy or beyond. This is not a plea based on sentimentality, but on a staggering scientific assessment of rarity. We are the caretakers of a cosmic accident of incalculable value. The science from our neighbors is not permission to squander our inheritance. It is an urgent mandate to protect it with everything we have. Finally, this discovery bestows a somber, luminous dignity upon our condition. The Copernican principle taught us we are not the geographic center of the universe. Modern astronomy taught us we are not made of special stuff. Yet, Webb's look at Alpha Centauri suggests that in the realm of complex, aware existence, we may indeed be central, not in location, but in rarity. We are the universe, in one small, privileged corner, becomes self-aware. The photons that struck Webb's mirror from Alpha Centauri traveled 4 years through the void. In that same void, our own radio and television signals, our own testament to consciousness, bleed outward at the speed of light. They will pass through the sterile systems of Alpha Centauri and continue into the deep, meeting only dust and quiet stars. For thousands of light years in every direction, our signal of existence may be the only one. And so, we find ourselves in a new kind of universe, not one teeming with life, but one where life, and especially mind, is the most precious and precarious of exceptions. The search will and must go on. James Webb and its successors will scan thousands more worlds, and we may yet find a biosignature in the atmosphere of a distant, single, quiet star. But even if we do, the overwhelming message of our nearest stellar family will stand. Habitability is a narrow ledge over an abyss of sterile physics. We are alone on that ledge. For now, and perhaps forever, the conversations we have, the art we create, the science we pursue, the love we share, and the future we build, these are the only conversations, the only art, the only science, the only love, and the only future in this vast neighborhood of stars. The science from Alpha Centauri is not an ending, it is a beginning. It is the beginning of our true cosmic adulthood, where we look out at the magnificent silent darkness, understand our incredible luck and profound responsibility, and turn our attention back to the only place in that darkness where we know light and mind exist. Here, now, on this pale blue oasis, the greatest story in this part of the galaxy is still being written, not out there, but by us.